Okay, we are back to the uh, original paper of George Bernard Danzig again, okay, for the linear programming under uncertainties. Okay, as we have learned from the previous two examples from the paper, okay, and we also expand the knowledge that we learned from these two examples for and from the last clip I already give you another example that show the resulting model that can be extended to a very large LP model, especially for the more practical aspect where the number of uncertain variable has a lot more than the previous example. Okay, but again with the example that Danzig gave in the second example, he only consider only one parameter, uncertain parameter. Okay, as you know that you have more uncertain variable with the combination of uncertainties, the number of scenario, even you try to approximate it as a finite, it still can lead to a very large number of scenario, and that resulting model from a small model can be you can try an example that can increase to a multi-million number of variable and constraint. Okay, and as I refer to you again that uh, this problem is like that, how much you're gonna sample from the large number, the large size of population, that even the large sample lead to a large problem. So only one lucky situation is that the problem still maintain the linear programming model. Okay, hopefully we can solve it with the existing technology that we have nowadays. Okay, but at this moment we're going to move on to the next example that Danzig gave in his paper. Okay, that's on the third page of the paper. In this case, he expand to, instead of the two-stage case, to the three-stage case. Okay, you might remember the equation from the first stage, right? Originally you have 100 ship item, okay, equal to the number that you're gonna buy, and then the supply will give it to you, okay, plus that's x of 1 plus x of 1 2, which is the safety stock or the inventory you need to keep it. Okay, and then it come up to the second equation here, okay, of d sub 2 equal to x of 1 plus x of 1 minus x of 2. We already explained this, that okay, since x of 2 is the inventory to keep, okay, the only amount of supply to satisfy d sub 2 is x of 1. Since d sub 2 you don't know the exact value, okay, in advance, okay, but you can estimate that the range that, okay, is can happen between, I think I illustrate, give you an example between 70 to 90, but in the example, based on what Danzig gave, is that okay, the unknown demand uniformly distributed between 70 and 80. Okay, so there come the third equation here, which is the minimum demand of 70. Look at this relationship, equal to minus x sub 1 2 plus x sub 2 3 plus x sub 2 4. So what's happening here, okay, with this equation? Let's look at the meaning of this equation. Okay, he identified x sub 2 3 is the number shipped, product shipped from factory in the second stage. In this case, stage can be period. Okay, okay, this is the first period, the demand of the first period. The first stage is at the beginning. Okay, and x sub 2 4 is number you want to keep it uh, at the end of the first period. Okay, so you know that, okay, here the relationship is that x sub 2 3 is the one that coming. Okay, but x sub 1 2 is minus. What is the minus x sub 1 2 mean? And then plus x sub 2 4. Okay, x sub 2 4. Okay, you have to know that X sub 1, 2 is the inventory that you keep it in the first stage. Okay, so you already have this on hand. Okay, on hand. Okay, so 70 is the minimum of demand, minimum demand that can happen. Okay, okay. So with 70 is the minimum of demand that can happen. Okay, X sub 2, 3 is that is the decision you need to make is the number of product you ship from the factory. It's different from X sub 1, 1. X sub 1, 1 is to meet with the 100 here. Okay, to meet with 100 here. But 70 is the demand here. Okay, it's not the minimum demand for D sub 2. But 70 here is identified as the number that you produce on second stage. Okay, the number that you produce in the second stage. Okay, the first stage you get the product 100 unit. The second stage you're going to produce the product 70. Okay, if you move X sub 1, 2 to the left hand side, you will know the meaning that 70 plus X sub 1, 2 is the availability, is the total number of product that you have. Because you want to produce 70, and X sub 1, 2 is the one that you keep from the first stage. Okay, so the total of 70 plus X sub 1, 2 is the amount that you have. It have to be equal to X sub 2, 3. X sub 2, 3 is the number that you ship from the factory. Okay, ship to the factory. And X sub 2, 4, what is X sub 2, 4 here? What is X sub 2, 4 play the same roles as X sub 2, 2, okay, or X sub 1, 2, sorry, here. Okay, it is the amount that you want to keep. Okay, look at here, 70 plus X sub 1, 2 is similar to what you have is 100 you have on hand. 70 plus X sub 1, 2 is the one that you have on hand. Is equal to X sub 2, 3. X sub 2, 3 is the number that you want to ship, and then you add X sub 2, 4, play the same role as X sub 1, 2. Is the number that you want to keep on the second stage. Okay, so that's the meaning of the relation of the equation here in the second stage after the uncertain equation on D sub 2 previously. Okay, and now in the third stage you have a new demand, the uncertain demand we call D sub 3. Okay, D sub 3 have to be equal to what? It's the same as X sub 1, X sub 2, 2 here. You might remember that X sub 2, 2 serve as the exceeding amount when X sub 1, 1 already fulfill the requirement of D sub 2, right? Suppose that X sub 1, 1 is more than D sub 2, therefore you have X sub 2, 2 as a positive value. So this one is the remaining product that ship back and keep it at the store. And we didn't count it as an inventory cost. There's no additional cost or anything. But this one have to be the one that you have inventory on hand, X sub 2, 2. Plus X sub 2, 3. X sub 2, 3 is the number one, there's the one that you ship it to your customer. It's the same row as X sub 1, 1 here. This one is X sub 2, 3. And then with the uncertainty of D sub 3, therefore you need to add, this one is like U minus V, plus X sub 3, 1 minus X sub 3, 2. Because you know that X sub 2, 2, the on hand plus what you're going to have, X sub 2, 3, okay, can either exceed or less than D sub 3. Because you don't know D sub 3. D sub 3 is uncertain demand. Therefore, you need these two variables to balance and keep the relationship as a linear equation. Okay, so this one is become what we call the multi-stage case. The randomness can keep going on stage by stage. Okay, and you can see that with example 2 and example 3, there's a major difference from the example that we gave from your last clip. Is that you saw here, you say X sub 2, 1 and X sub 2, 2 is like U, V. This one X sub 3, 1 and X sub 2, 2 is like U and V. But you look at minus V here, minus X sub 2, 2. With the third stage, X sub 2, 2 is used again. It will be different from the example I gave you last time. Is that for each equation, for each scenario, U and V are all separate, independent of each other. Okay, but this one is like minus v here, you have plus v in the next stage. So in this case, the methodology that we're going to cover in the lecture 1 will not cover how to handle this case. But if you keep going on and watch lecture 2, there will be a solution for this type of problem. But this one is another example that show you can see that from the two-stage problem, it can keep going on to become a multi-stage problem. Okay, and then Danzig, what nice thing about Danzig as a writer that he always illustrate by example. And within this example, sometimes if you can be able to understand it, you can see that he really trying to make the idea much more easier for general people, not only mathematicians, to get into what he have in mind. Okay, and for the example 4, he referred to, you might remember from the first page that I called that the motivation to write this paper happened when he was stimulated by discussion with A. Ferguson. And with Ferguson talk come with the illustration for the example 4. Example 4 is the original of the transportation problem. Okay, with equation 6 and equation 7 is a well-known linear transportation problem and can be formulated not only in LP model, it can be like a minimum cost network flow model also. Okay, look at the equation here. Okay, he represents x sub I j as the amount of transportation from supplier I to customer j, where a sub I is the total number of supply unit, okay, in each side k, okay, in each supply I. And the equation 7 is the demand size. Okay, he add this one, sometimes b sub ij is equal to 1 for all ij in the classical transportation model. But this one he write in a more general form that suppose the unit of supply and unit of demand have a different unit. There are some transform, either gain or loss, whatever. And b sub ij is used as a conversion of unit of xij. Xij is the unit is according to the supply side, and then when the demand side have a unit of u sub j here. Okay, b sub ij times x sub ij become you need b sub ij as a conversion coefficient here. Okay, for this one in the supply side, the total summation, okay, of the product converted to the demand unit, okay, from all supplier from I to M, okay, must equal to this one we call u sub j. This one will be the amount of supply that we can give to customer j. Okay, so this is what we call the constraint here. But the uncertainty of Danzig's Pareto rule here from equation 8, when d sub j, suppose d sub j here is the amount of demand at supplier j. Okay, d sub j here. And then you know that u sub j is a supply size converted to the demand size. Okay, if we already know the exact value of d sub j, okay, so you don't need the variable u sub j. You can just put d sub j over here instead of u sub j. But Danzig separate this equation because he want to add the assumption of d sub j, that d sub j is an uncertain demand over here. When d sub j is uncertain demand, okay, with the decision that you make with x sub ij here over here, you only know that, okay, once I make decision of x sub ij, this the amount of output to satisfying the demand of the customer is only u sub j. But you don't really know whether u sub j will fulfill the requirement of d sub j or not, because d sub j can have so many scenarios that can happen. Therefore, you need to add another variable called v and s here. You can see that the notation he used is different from example to example. Like in example 2 or 3, you can see that x sub 2 1, x sub 2 2 is become like uv in our model. This one x sub 2 1, x sub 2 2, x sub 3 1, x sub 3 2. Okay, but now when he moved to this example, the roles of the plus minus additional variable u v and s. But in our model, okay, our notation that we use in the model from the example I showed from your last step or for the original uh, PowerPoint, okay, I've used u and v, okay. So I can understand that you sometimes you confuse with the way people use the notation. That's the way to live when you live when you read the mathematical paper. Okay, you need to understand and realize that how the author utilize the representation of each variable in the model. Okay, over here, okay, U sub j is a total supply from the deterministic from the certain point once you already assign dx sub by j. But you don't know d sub j here. Therefore, there's a risk that u sub j might not fulfill d sub j. So you need to add if u sub j is less than d sub j, and you need to subtract s sub j in case of u sub j is more than d sub j. Okay. And the definition of V sub j in reality we call the shortage of supply, and S sub j is the excess of supply. Okay, therefore the total cost function over here, okay, he can add over here that for each customer j equal to an n is the number of customer, m is the number of supply. Okay, over here. Okay, and you can see that in this case, he didn't have any cost when you have excess, the demand, the supply size, the amount of supply size is greater than the demand size. But in reality, you might call that is that you have an inventory cost. But in this example, Danzig keep consistently use the same format as he recall from example 2, that there will be only cost when the supply is less than demand. You need to fulfill the demand by, solving the shortage problem, finding another supply additional. You want to buy it with more expensive cost per unit. This one is also the alpha j in V sub j over here. And certainly V sub j here, when D sub j have an infinite number of possibility, leading to V sub j and S sub j have an infinite number of additional variable also. And also, if we can approximate d sub j as a finite dimensional space, but or mean the finite number of scenario, okay, v sub j, okay, for each j have another additional variable equal to number of scenario of d sub j, okay, and this is another extension of the previous 3 example lead to the 4 example. From the modeling point of view, okay, an example is finished here at equation 9. But after this, it will be more of a mathematical resource, okay. So I'm not gonna try to prove or explain you or any proof that Danzig tried to propose, but just to inform you that originally Danzig is a mathematician. Okay, he got a PhD degree in statistics, mathematical statistics. Okay, so it is nature that before he established any knowledge, he need to write a proof. Okay, so after this, he gonna try to illustrate his proof. Okay, and before the end of this session lecture, okay, I'm gonna go to the first theorem that he's trying to establish first. Okay, first of all, he finished the model with equation 9 as the objective function here, okay, as an LP. Okay, but in reality, okay, suppose d sub j is continuous, okay, a random variable is in the infinite space. Okay, he would assume that the objective to minimize the total expected cost, okay, he refers this as a notation first, as this one, okay, the phi sub j, given d sub j, you get u sub j, okay, when d sub j and then you get u sub, you're making a decision of u sub j when d sub j is known. Okay, not making decision is that the effect on the u sub j once d sub j is known. This one is phi sub j u sub j given d sub j be the minimum cost at destination j if the supply is uj and the demand is dj, d sub j. Okay, so you just write this statement. It is clear that equation 10, okay, phi j uj given d sub j is equal to alpha j d sub j minus u sub j, which is gonna be this one v sub j, because this is the case when d sub j is greater than or equal to u sub j. And then when d sub j is less than u sub j, in this case, there'll be no cost, which is what happened. In this case, you're going to have s sub j instead. But in general, you might have a cost here, maybe another beta sub j of u sub j minus d sub j. Okay, that can add it up. But this one, Danzig just try to maintain and be consistent with this notation and that he have been used in from example 2. Okay, it says where alpha sub j is the coefficient of proportionality, which is the constant value, the coefficient that you. We shall now give a result due to Scarf. Scarf is also a famous intellectual in economics and have been using linear programming to solve a lot of important problems in economics. Okay, he established the first theorem is that this function of phi sub j equal to alpha j d sub j minus u sub j, and he just gonna denote it by phi sub j u sub j, just cancel given d sub j, because you want to say expected value. Okay, so why expected value is that once you already know d sub j, okay, the remaining possibility is only for u sub j. Okay, so we just want to prove that this expected value is a convex function of uj. You say this is more, we're really getting deeper into the mathematical zone. Okay, and certainly we give the definition of probability density function, and then he tried to prove that this is the way he tried to prove is that he tried to prove that the density function of phi sub j, u sub j, the first derivative has a negative sign, so that he can prove that the first derivative is non-decreasing function, and then he proved that for the second derivative of u sub j is always greater than or 0, and that's the property that can prove that this function is a convex function. It will be very difficult for you to understand this, but this is the way the mathematics people know. They use property refer to each other to confirm some of the mathematical facts. Okay, but I'm going to give you the reason that why Danzig proved this theorem. He proved this theorem just trying to show that this the equation 9 is a convex function. Okay, and once it's a convex function, as you know, in other way you can prove this because this is the what we call the linear equation. So a linear equation can be either convex or concave function at the same time. That's also another mathematical theorem that I refer to. But in this case, he tried to generalize it. You look at the way he proved it. He generalized it such that d sub j can be continuous random variable. Look at the possibility here for when he find the probability density function of d sub j. Okay, phi sub j is classified in the state that p of x is used for cumulative function here. Okay, from when x start from u sub j up to infinity. So therefore, the real definition of this probability density function, you already refer that d sub j is a continuous random variable, can be infinite number of scenario and alternative. And he's trying to show that this, when you consider in the infinite solution space, is already a convex function also. And also he expand the theorem here for another lemma to say that if you have a multi-variable, when multiple decision making variable x sub 1, x sub 2 to x sub n at the same time, given a parameter theta, which is theta is a random variable here. It's the same as you use here. D sub j is random variable. Okay. No matter how many variables you add it up after you given a random variable theta, phi is always a convex function over a fixed region ohm here. Okay, omega here. Okay, and you might say, oh, this is too much mathematics, but I just give you the only reason that Danzig's trying to prove this. He's trying to prove that at the end, the expected cost here is always a convex function. Either you extend this problem to an infinite space or not. Okay? But if you fix it within a finite space with linearity that illustrated by example, you can easily prove that it's already a convex function. But a lot of people say that, who care whether they're a convex function or not? Okay, because if you would like to minimize a convex function, you have an opportunities, okay, to guarantee the global optimum solution instead of the local optimum solution. That basic optimization theory for either both linear and nonlinear situation. And Danzig might consider this that even though phi here, okay, can be nonlinear. Let's just say nonlinear. Okay, even alpha j. Actually, when you see it here, it's already look like a nonlinear function. It's a step. You can be since it's already 0 when dj is less than uj, and you have this one a linear cost when alpha j d sub j minus u sub j when d sub j is greater than u sub j. So it's only linear in the first interval, but then with the step down to 0 with this, the whole function of phi j is not a linear function. It's a kind of piecewise linear function. Okay, so that's it, just to show you that with the extension of this definition, the whole function is a convex function. Okay, and you can extend it. Okay, and also here, the equation 15 is what I already confirmed to you, that the basic theorem, the expected value objective function here that we already give. Alpha j, you remember that we have additional variable of v sub j, but in general it can be phi sub j, u sub j here. Okay, and this is what we call always be a convex function. Okay, and also if this according to become a single variable, it become a linear programming, and you can use the next paragraph is that this permit application of a well-known device for approximating such a problem by standard linear programming problem. Okay, in the case the objective function can be represented by a sum of a convex function. Okay, this one he referred to the problem work from Chance and Limke. Okay, and look at he tried to explain here that this is a type of convex function. Okay, it have keep increasing but also maintain the convexity properties. Okay, but certainly this is just to illustrate a function, but the key result that we really want is the whole model, okay, approximated as linear programming, okay, is solvable, okay, and can provide once if you keep increasing the size of the problem, give you a better approximation approaching the population data. This expected value, okay, will always converge to the population results. Okay, so that's the importance of the proof that Danzig gave in the first place. And you can see that equation 19 is always important, that you can approximate the infinite space here, okay, by finite space here. That's the way he explained way back in 1955, but then I gave you the example that nowadays we use this approach to explain in the example from our last clip. Okay, and then move to example the two-stage with general linear structure. Okay, and certainly all of this, the only one reason that he want is that he want to establish that the resulting model of the problem you're working on with uncertain randomness in some system parameter, you still be able to maintain the linear programming structure. Okay, this one he refer back to example 4, as I told you before. This is the supply side, so as you might remember. Okay, this one from equation 6, this one from equation 7. Okay, instead now he already erased the u sub j. You go back and look at equation 6 and 7 again. This one 6 and 7. Okay, in this one you erase these u sub j because u sub j you put it in here with equation 8. So you just use equation 7, substitute u sub j by the left hand side here over here, then you get this one. Okay, yeah, with the additional of plus and minus to balance the uncertainty of d. And then with this objective, expected cost objective function, the uncertainty of Cij, you can use example 1 by using the expected value of C sub ij. And then the uncertainty of D sub j leading to additional expected cost of alpha j Vj, where V sub j is an additional decision variable, and alpha sub j is a constant proportional to V sub j, the amount of V sub j. Okay? So that when he finished here, he already finished what his discussion with Ferguson, because this is the problem that Ferguson raised, and then Danzig provide modeling and notation to expand this, and he proved that he still can maintain the problem with additional of uncertain element. He still be able to maintain the linearity of the model. Okay, and this one is even go further. Okay, I'm not going to go to this, but this one is very important to when you study what we call try to partition the problem, and using the idea we will give lecture in the next couple of clips that about Bender decomposition, and then after that we will come back to this theorem again. Okay, but we as we move toward the end, and this one you can see that from two-stage to multi-stage, that's according to example 2, from example 2 example 3, that we can always expand this problem to a multi-stage problem. Okay, and certainly he tried to develop a general theorem for the multi-stage problem, as we will come back and then try to look at this one. This one is also the shipping problem revisited from example 2 again. Okay, try to illustrate the theorem that he established here. Okay, the theorem here that I skip at this moment, but we'll be back and try to look for it. But this one is just give this example that, okay, you can see you can separate the problem. This one you try to minimize the first stage, the x sub 2 one, and then after you know the x sub 2 one, you extend to try to minimize expected over here. Okay, you go here and try to find the minimum value by now your decision variable is only x sub 1 1 here. Okay, once x sub 2 1 is already established. Okay, and I think that this part play a major role for, because you have to understand that Danzig, one of the reference that Danzig uses is using the reference of Bellman of dynamic programming. This is just my own opinion of reading this paper, that even he refer over here that he felt that once you be able to partition the problem to multi-stage problem, the best solution approach should be, at that time, Bellman started to establish the philosophy of dynamic programming. So Danzig have a strong belief at that time that dynamic programming might be the solution to solve this multi-stage or even the two-stage problem. But as time goes by until today, this is not such a case. Okay, dynamic programming didn't work well with the multi-stage problem. If I still remember, I will discuss you about this. But when you read this paper up to this paragraph, you know that Danzig saw potential that using dynamic programming to solve. That's why all the theorem that he proved coming from this one, okay, unto this one, just trying to support the use of dynamic programming. That's just only my thought. You have to read it yourself and then try to understand it, okay? And we go forward to the summary of this paper at the end. He considered that with the number of possibility here, okay, of the chance vector of the right hand side with probabilities, okay, he said that it is not difficult to obtain a direct linear programming solution for small k. Okay, say k is equal to 3, okay, for small size problem. Okay, which means that you only have 3 alternative, p sub 1 to p sub k. But the paper didn't say that when you're dealing with multivariate random variable, the all combination and number of scenarios, which means the k is much larger value. Okay, that leads you to, even though you still maintain the direct linear programming solution, you end up having a very large scale problem. Okay, how large can it be, and how the technology nowadays can be used? Okay, we will show you in the next clip when we're trying to apply the current technology, which is we call the spreadsheet modeling, to solve this type of problem that formulated way back in 1955. Okay, I hope you this part is maybe the most difficult part to explain, but since this is a classic idea, we gonna come back to this paper for some more detail. But I'm trying to simplify the content as much as possible. Okay, so for this part, I'm gonna finish it here. See you later.